June 29, 1995. It is a busy Thursday afternoon in Seoul. Customers move through the Sampoong department store. Staff remain at their counters. Escalators keep running. From outside, there is no obvious emergency. Inside, the fifth floor ceiling is cracking. Civil engineers have inspected the damage. They have warned that the building is at risk of collapse. Management has closed the upper floor, but the store itself remains open. At 5:55 p.m., the north wing collapses. In approximately 20 seconds, 5 stories fall to basement level. 502 people are killed. 937 are injured. 6 remain missing. This is not the story of one defective column. It is the story of a building changed again and again, until one connection could no longer carry what had been placed above it. This is the structural autopsy of the Sampoong department store. Construction begins in 1987. The original plan is for a 4-story residential building. Its columns, slabs, loads, and internal layout are calculated for that purpose. Then the owner changes the project into a department store. Retail space demands larger open floors. Walls move, circulation changes. The load carried through the building changes with them. The original contractor refuses to carry out proposed structural modifications because of safety concerns. The contractor is dismissed. Construction continues under the owner's own company. By the time Sampoong opens, the building no longer matches the structure its original engineers intended to build. To shoppers, none of this is visible. The store becomes a commercial success, attracting an estimated 40,000 visitors a day during its 5 years in service. But the building beneath them is not simply the original design with different signs above the doors. It is a different structural proposition. Sampoong uses flat slab construction. There are no deep beams beneath each floor. Instead, the reinforced concrete slabs rest directly on columns. The system creates the wide, open spaces a department store wants, but it also makes the geometry around every slab column connection important. The inquiry would later compare what the calculations assumed with what had actually been built. The columns supporting the 5th floor and roof were calculated at 800 millimeters in diameter. They measured only 600. The effective slab depth in critical regions was specified at 410 millimeters. It measured 360. The concrete was specified at 21 megapascals. Tests found strength closer to 18. Each difference removed part of the intended margin. And at column lines 4 and E, investigators found something else. A drop panel, a thickened area of concrete intended around the column, had not been constructed. Where the slab was intended to be 450 millimeters thick, it was only 300. The building was not carrying one error, it was carrying several. The 5th floor had originally been designated as a roller skating rink. It became a restaurant level instead. Walls and false floors were added, but the structural system was not redesigned for the change. The inquiry calculated that the permanent load on the 5th floor increased by 35%. Above it, the roof also carried more weight than the calculations assumed. The lightweight roof topping had been calculated at 1.9 kilopascals. The installed topping imposed about 4. Then there was the cooling tower. After complaints from residents on the east side, it was moved toward the west. It was not separated into smaller units for the move. The inquiry found that moving it damaged the roof slab. Its weight also introduced unbalanced forces at the slab column connections below. By then, the building had changed in 3 different ways. Its structural dimensions were smaller than the calculations assumed. Its materials and slab depth provided less capacity, and its upper floors and roof carried more permanent load. Still, the building remained standing for almost 5 years. That survival could look like proof that the changes were acceptable. It was not. In April 1995, cracks appear in the 5th floor ceiling. They do not disappear. By the morning of June 29th, the cracking has increased dramatically. Management closes the top floor. The air conditioning is shut down. Management does not evacuate the store. The unusually high customer count and the revenue that would be lost by closing form part of that decision. Executives take the precaution of leaving. Customers and staff remain inside. The physical warning has now become a management decision. The cracks show that the structure is in distress. The inspection gives that distress meaning. The building is still occupied because the warning is not acted upon. At 5:55 p.m., the failure begins. The Committee of Inquiry traces its starting point to the 5th floor restaurant level at column 5E. Not every column fails at once. One critical slab column connection fails first. Only after the collapse does the engineering mechanism receive its name, punching shear. In a flat slab, the weight of the floor is transferred directly into each supporting column. That force is concentrated around the column's perimeter. Imagine pressing a narrow support through a sheet. The sheet does not need to split from one edge to the other. It can break locally around the point carrying the force. At column 5E, the concrete slab fails around the connection. The support provided at that point is lost. The load does not disappear. It is forced into the surrounding structure. Connections already carrying reduced margins are asked to accept more. Further failures follow. Slabs fall onto the floors below, adding dynamic load to a structure already in collapse. A local failure becomes progressive collapse. The north wing falls to basement level in approximately 20 seconds. When it stops, 502 people are dead, 937 are injured, and 6 are missing. At the time, it is the largest peacetime disaster in South Korean history. The collapse leaves an obvious question. How can a relatively new building fail without an earthquake, extreme weather, or an explosion? Investigators examine the collapse pattern and the ground conditions. They test concrete and reinforcing steel recovered from the site. They review design documents, construction records, and management reports. Then they analyze the structure. The evidence does not point to one isolated defect. It reveals overlapping failures in design, construction, loading, and management. The columns were smaller than the calculations assumed. The effective slab depth was reduced. The concrete was weaker than specified. A required drop panel was absent. The restaurant conversion increased the 5th floor dead load. The roof carried more load than assumed. Moving the cooling tower damaged the slab above the area of failure. And when visible distress became severe, the building was not evacuated. None of those facts replaces the direct mechanism. The collapse still begins with punching shear at a slab column connection, but the mechanism explains how the building failed. The evidence chain explains why that connection had so little capacity left. Roof-topping and cooling equipment imposed greater loads than the calculations assumed. Serious structural distress was identified, but the occupied store was not evacuated. One local connection failure triggered progressive collapse of the north wing. Sampoong did not fall because concrete suddenly changed its behavior. It fell because the conditions around one critical connection were changed repeatedly. Less column, less effective slab, weaker concrete, missing thickness, more load, then visible distress without evacuation. The final failure took approximately 20 seconds. The decisions that prepared it took years.